So I'd like to, so we're starting this session, and this session is exploration concepts. And we're going to start it off with a talk on radiation in the outer solar system by Bennett. And feel free to take it away.
Okay.
Thank you.
Thank you very much. And thank you for inviting me. Yeah. So like a few people I was roped into giving a talk. Come on. And he told me to be, what was it, controversial, confrontational, something like that. So I'll do my best. So I have the obligatory Centaur picture. This was the first one that came up, and he happens to be exploring, which I think is quite appropriate. Centaurs. Okay, so I'm going to start off with a very silly idea that hopefully all of you can debunk in your heads almost instantaneously. If we have a car exhaust, what are the three most common things that come out of that car exhaust? CO2, H2O, and CO. What do you put into your car?
Money.
Money, yes. It is a complex mixture of over 500 different hydrocarbons. It changes all over the world. It doesn't matter what you do, you get out of it. Oh, there's no laser. CO2, H2O, and CO. There is? Oh, Centaur.
No.
Ah, very powerful. Okay, we'll probably ignore that. But okay, it doesn't matter what you do, combustion, you get the same three things, because it turns out CO, CO2, and water are some of the most stable things that you're going to have. Okay, so my question is, oops, I've ruined everything now. It's all gone. What did I do? Oh, apparently, okay, there we go. So yeah, so you have these things. I'm going to ignore H2, which is like one of the larger things from the comet too. You have the same products. And so the question is, are you really observing what you are observing? Because there's been a lot of talks of like how most of the last session was devoted to, we're seeing CO here. We shouldn't be seeing it at this temperature. We're seeing CO2. It shouldn't be at this temperature. Maybe it's not. It's basically the point that I'd like to sort of say. So in particular, we've talked about this a little bit during this conference. This was the discovery, you can see it here, of O2 that they detected at Rosetta. And this caused a lot of controversy because we were like, well, how can there be O2 in there? That's a hypervolatile species. It should only be there at about 20 Kelvin. And this was observed at, I forget what it was, about 1 AU or something like that, maybe 2 AU. So this was controversial, about 5% O2 in there. Where did it come from? And the solution is, a lot of people are saying this must be interstellar for that reason. It must have been preserved, and it must have come all the way through. And then they're confused why there's not as much CO and other things like that, right? So one of the other areas that I work in is the field of astrobiology and the origin of life on Earth. And what I'm frustrated by is this idea that we have to etch-a-sketch every single time. We have to reinvent the wheel. So if you start from the Earth, people are like, oh, how can we get all these organic molecules on Earth? Maybe it was from the lightning or from the ocean or something like that. And we get to comets, and people are like, well, we have to start from nothing. How do we get to these molecules? But the fact is that you have the interstellar medium, and you're forming a solar system, a large number of the molecules survive. And this has only recently been shown, which you can't see down there, but Hinsley in 2011 showed about 50% of the material from the interstellar medium should survive the solar system. And there are a few other models with similar numbers. That's a large amount. So that means you don't have to have all your pristine material that these comets represent might actually be quite evolved and might be chemically complex, rather than just being the simple things CO2, CO, CO, etc. Okay, so this idea, try and be like, maybe don't do that. But in answer to the question about how you should all be able to debunk me, but we know that there is a lot of CO, CO2, and H2O in these comets, even if it comes from an interstellar source, is because we have down here, this is an infrared spectrum. And it's taken much the same way we do in the lab. You have a field star, which is a black body. Some cloud gets in the way of it, and then you have your fancy telescope, maybe in 20 years, James Webb, and you can detect here CO, CO2, all these kind of things. 2026, right? I don't know when it is. Yes, so we know that there's a lot of CO, we know there's a lot of CO2, we know there's water a lot in there. So it's not unreasonable you should have these things as comments in your comments, right? So in the interstellar medium, we know there's a lot of organic molecules that have been discovered. This is way out of date. There's probably close to 300 by now. But a lot of them have like, this is the number of atoms. So they're like reasonably complex. Okay, so we can see things like oops, I don't know what I'm doing with that, but, but there's even things like glycine. Okay, so like this is like tentative detections of glycine, I should say. And so in this case, what happens is you have a young star that forms, and as it forms, you have a very similar sort of case that you have ices around the star, and as based on the volatility, you have these different species that are desorbing. Very similar situation as a comet. And what tends to happen is around these young stars, you get all of those molecules being observed around the time that the methanol is coming off. And so again, people in this community would be like, oh, it must be the methanol. It can't be the fact that you have the ice itself that's being irradiated that's forming all these molecules. So if you look at the inventory of comets, and this is definitely very far out of date, because this is pre-Rosetta, but the compositions are very similar. We have a similar level of complexity. And we know that like they get closer to the sun, more of these molecules come off. I don't know what it's doing here. OK. And so just to very quickly point out that they have actually detected glycine in a bunch of comets / Centaurs. So I heard people referring to both of these as Centaurs, but I think they're just still comets, aren't they? Is one of them a Centaur? I'm confused more than I was before about what is a Centaur now. So
Both the Jupiter family.
Jupiter family comets, OK. But I thought we were transitioning. No, OK, never mind. So they're still comets. OK, good. So Comet Wild 2 had a frying pan flying behind the comet and actually managed to capture about a gram of glycine, which is about the amount of material, sorry, a gram of material, which is the amount necessary so you can tell that it's not terrestrial glycine based on the isotopes. So you capture quite a lot of material. This is the Rosetta Cosmo instrument. You can't see that, but that's actually the exact mass of glycine that they detected in the coma. So to talk about the different radiation sources, essentially there are two main ones we want to worry about in the outer solar system. The first is the sun, which is essentially, this is supposed to be the energy, the energy of the protons. This is actually oxygen, but it's the same thing. Most of them are around about 1 keV in energy. And what that means is they're not going to be very penetrating. They're going to just irradiate the outer surface layer. And so this is an example from the moon of space weathering. You can just see like this outer layer has basically been irradiated and it's changed its composition, its morphology due to that radiation. And it forms this nanophase ion. And a lot of the effects that they see in asteroids are the fact you have like a red slope, decreased albedo, and decreased band depths. And I also want to point out that that is perhaps not the case if you're looking at ices, if you're looking at a different part of the spectrum, et cetera, et cetera. So like these things are not always true. In the outer solar system, we have to be more careful about galactic cosmic rays. So they get modulated as you come into the solar system, so there's less and less of them in the inner solar system. These are very, very high energy. So, oops. These are more like 1 to 100 MeV in energy, okay? And so they are therefore very, very penetrating. What they can do in the atmosphere is they start these cascades of particles that come down, and you can even like do experiments on relativity if you want to. Okay, so I want to give a very brief overview of this radiation process. So essentially, if you have an ion coming through an ice, it releases, because it's ionizing radiation, it releases a whole bunch of electrons. All these graphs I'm going to show you now are going to have probability on the y-axis and something else on the right, usually energy. What this plot is showing you is just that essentially we can ignore the fact that it's a proton and just treat it as an electron. I'm not going to really get too much into it. This next one is important, though. This is showing you that no matter what your energy of your ion, you're going to end up with a distribution of electrons that have an energy of 10 eV. Okay, so that number is going to come up later on. All this graph is showing you is that if you have photons of different energy, they're going to make electrons. They're also ionizing. And this last graph, so just to say that the penetration depth of MeV giga-electron volt particles is of the range of meters. So what you can't see here, this is energy of an electron versus probability versus what species are made. And so you might think if you have ionizing radiation, you're going to mostly make ions. And that is true. But if you have 10 eV electrons, you mostly make radicals. So all of our chemistry that we're actually going to observe is going to be radical-induced chemistry. And that's good because things get complicated if you have very high energy things and super thermal chemistry. I'm not going to break this down because there's not time, but the two things that I should say about this graph is if you have a lot of barriers between different reactions, if you have radiation, you can overcome any barrier. If you're at cold temperatures, 10 to 40 Kelvin, any intermediate or unstable species you have can be stabilized. So in short, we're going to have a lot of weird molecules that can be formed by radiation, and they're going to be stable only at low temperatures. Okay? So this is very, very complicated stuff, but let me break it down for you. If you have methane, you can break it into CH3 plus a hydrogen. If you have ammonia, which is NH3, you can break it down into NH2 plus a hydrogen. The hydrogens can react with carbon dioxide to make HOCO or something like that. These two things, the methyl radical and the amine radical can combine to make methylamine. Similar things can break apart, reform together. Eventually, you end up with glycine. So this is a very simple way that you can get glycine in these sort of experiments. OK, how long do I have left? 2 minutes? OK, excellent. So I'm going to skip past this bit for how we do this in lab. We do this in lab. We have a setup. It's real. There's a photo. Essentially, what we do is we recreate these conditions in a lab. We cool it down, we irradiate it, and we observe these species in the IR and with the mass spec. And just to give you an idea, this is CO. So black is before radiation, red is after radiation. And this is going to be a disaster if I do it with this thing. I'm just going to put up all these different species that we observe. So CO2, C3O, C5O, C6O, C3O2, blah, blah. You get a lot of complicated species. C3, you observe some of these species or similar species in comets. If you do the same thing with CO2, you get CO, we get ozone, we get CO3, CO4, CO5, CO6, a lot of weird things. As I said, these are not stable at room temperature. I'm going to skip over the calculation things. So there's ways you can prove this in the lab, and we could say that this is actually happening. One thing, this is the last thing I want to point out that's kind of maybe important, is what happens when you make these larger molecules is they become less volatile. Okay, so you're making things like this is, I should put these up. Oh, it's all gone wrong. Okay, so what's happening is we have, these are clearly from the same molecule. Okay, so we've got an ice, we've irradiated it, and now we're heating it up. And we're observing two different species that have a difference of mass 28 for CO. And so this is not the temperature CO comes off at, but we're observing it at between 100 and 150 Kelvin. And it's releasing CO into the chamber. Does anyone follow that? You can ask me questions later. And that's as far as I wanted to go for this. We also did some stuff on sputtering of things, and if you ever have a mass spec, you kind of want to be careful. Oh, this is my fabulous animation skills. I can talk about that if there's later. I can finish. Just leave you with some questions. But basically, the idea is that if you have things like CO3, which is produced in high abundance when you radiate CO2, you can get CO and O2, and that's maybe a way to get these hypervolatile species. Yeah, I think I'll leave it at that. Any questions?
Great. Thanks, Chris.
Gus Reed, FSI. Awesome, Chris. Thank you for indulging me with your talk. So if we focus on the Centaur region, we are kind of far, we're kind of far from the sun, so there's less energetic particles from there. We're not yet at trans-Neptune or far enough from the sun to be, to get a lot of galactic cosmic rays in. So what's a dosage you would need, for example, to follow this route of CO2 and end up with O2 and CO?
Yeah, so I glossed over that purposefully. Dosage is probably one of the worst units ever used in the world, because our experiments that we did had a dosage of about 2 eV per molecule.
Okay.
And we could see about 5 to 10% products. the calculations by Struzzulo et al. Say that you should have in the upper 10 meters of comets about 600 EV per molecule over 4.5 billion years. Okay, so if a typical bond is 4.5 EV, it's spent on like the time, what is the actual energy that you're inputting, right? You could put it at a very, very low level for a long time and you wouldn't see anything. Or you could put it at a very high level for a short time and you would see a lot more, but at a lower dose, effectively, right? So what is the dose that's important? It's not a good unit. We need to figure out a better unit to describe these things.
Okay, so I'll restate it then.
Yeah.
In your mind, is this process inevitable, or do you need some conditions in order for this to be a robust way to get O2?
Yeah, so it's not well constrained how much there would be in these comets right now, right? We don't know that. What we would need, but it should be there, right? Because we have this interstellar material that was irradiated that should have these things in it anyway that everything formed from. So it should be there no matter how far down in the comet you get. Probably the upper layer has also been exposed to more radiation. So we would have more of a chance of finding these kinds of things in those upper layers. And yeah, so I'd say it's pretty similar. So probably like the further out you are, the more galactic cosmic rays you've been exposed to. So more chance there.
There you go.
So it's not necessarily Centaur related, sorry. So you said that these complex organic molecules, they're maybe not at the surface because that was the surface and it got weathered, but maybe they're just survival molecules from the early stages of the solar system. So you would say that you would expect these molecules to be also inside of the body.
Yep.
And so what are these detectable concentrations? I'm not sure what detectable would be, but would that be, would the surface compositions that you see be representative of the whole internal structure of the body? Or is it just the surface that gets irradiated that has a different composition?
Presumably, if they're all pristine and all roughly the same material, like we assume for carbonaceous chondrites, right? So they should be there at some level.
Okay.
The trouble is that like how you detect them or not is going to be tricky because they're going to break down very easily because they're not very stable into other molecules.
But these are organic molecules are seen at the surface, right?
Sure. And some fragments of these or some of these molecules have actually been kind of observed. I'm not up with the latest Rosetta results, actually. I'm trying to find a nice overview paper on that. But.
So it's not my field. I thought they were observed on, very old surfaces also. So like on asteroids and stuff.
Right, yeah.
But you're saying that they would not necessarily survive a long-term exposure to a space
some of the
environment.
species I talked about in the ices would not be probably found on asteroids because they don't exist at those temperatures.
Mm-hmm.
They are only going to be like to extend that range of the hypervolatiles coming off at higher temperatures.
So these would be two different processes, the organic molecules that you would see in pristine material on comets and centaurs and stuff, and the organic molecules that would be seen on weathered surfaces on asteroids. These would be two.
So I guess things like amino acids you should get in both. Something like that, because that is a fairly stable molecule.
Thanks.
I think maybe we'll talk later.
Okay. Oh, sorry. Do you want to? Yeah. Last question.
Jordan Stuckloff, PSI. So this is fascinating. So my question is, have there been further studies to look at how much O2 we would actually expect to form?
So
I mean, obviously it's going to be constrained to be less than CO2, but
yeah. So the trouble is that if you irradiate CO2, you generate O2 anyway, and so what you have to do is you have to basically do a lot of tricky things in the mass spec to basically be able to deconvolve those two different things, the O2 from the O2 and the O2 from that CO3. Okay, so that could be difficult. It might be possible. But for example, what you might be able to do is if the CO3 is coming off and you use a much lower energy electron to ionize it, you might still be able to get CO3. For example, they've actually done electron attachment where you can see CO3 minus rather than looking at the positive ions. And so that would be a way that you could see it, at least in our setup. That would also be a way if you had a mass spec going to a comet with a negative ion attachment accessory, you might be able to see those molecules that way.
So I guess more specifically, I was trying to follow up on one of Alan's comments of, could we explain what was seen on 67P with this?
Yes. I mean, how do you mean? What those, you mean the O2 and the yes, probably.
With the quantity of O2 produced?
At 67P, yeah. 5%, probably. CO2, so CO2, you know, if you assume it's abundant at what, 20-25%, we get easily 5-10% CO3. And like we can get that from the CO2. And there's other molecules as well that might have more. There's actually like evidence that like the more you irradiate CO2, you get larger molecules that are less volatile, and those have like more oxygen in them as well.
Quickly. Yep, sure.
I'm not going to present my own paper here. Okay. Okay. So it is the model that you're talking about. Okay. Let me preface this by one thing. So if you take a comet like 67P, which is losing average 1 or several meters per orbit of material, are you talking about primordial oxygen that was created a long time ago through this process and trapped, or recent oxygen?
Actually, both. You would also be able to do that to some degree, but it would be hypervolatile, right? So you might not expect it at close anyway, or you have the same argument.
But it's 20 Kelvin, though. I mean, that's.
But the thing with non-safe, you're removing, so you're doing it and the surface.
So I'm asking if the time, if it's the latter, if it's recently produced oxygen through this process, do the timescales work for short period comets?
That's sort of what I was getting at. Yeah.
Yeah.
You're removing the layer.
Potentially, yeah, but then it still have to be trapped by something, right? So not to get out. And yeah, but it helps somewhat that problem, right?
Okay, so I think we need to. All right. Well, let's thank our speaker one more time. And the next speaker is
realize that
George Brueshaber. Sean Brueshaber. Sorry, Sean. Sorry about that.
You just reminded me.
Okay. Good afternoon. Are we ready to leave Earth, leave nice warm Central Florida, and actually go to one of these things? Because this is what this is about. Okay. In 2017, myself and 17 other people were selected for JPL's Planetary Science Summer Seminar. And through a coin toss, because the vote was split, we decided to study a Centaur mission. Okay. The other option was Titan. So we're probably happy we went with this one. Okay. All right, so here's our team of 18 postdocs and graduate students. Some of us have some small body background, some of us don't, like me. I'm a giant atmosphere guy, so this is all news to me, or new to me. And we came together in over a period of 11 weeks, including 10 weeks of telecons and literature research, and then 1 week at JPL, which was very intense, very fun, and no sleep. We put together what you're going to see here. And our paper has been recently published here. Sam Howell was our PI and therefore our first author. Camilla, a Centaur reconnaissance and impact mission concept. So basically, we're going to go to a Centaur. Before we get there, we're going to take pictures. When we get there, we're going to take more pictures, and we're going to bomb the thing with an impactor and take more pictures of the hole and debris afterwards, and then send the data home. Any questions? Okay. Okay, so I'm sure that you guys discussed this in depth yesterday, so I'm not going to spend a whole lot of time on this. What's a Centaur? Okay. Now, first of all, why Carliclo? Because this is where we're going. First of all, we looked at a lot of different mission possibilities even before we got to JPL, and there were 6 that we mentioned briefly in our paper. There were multiple flybys, including reconnaissance of multiple Centaurs. But because of the rules that we were under, which means we had to follow New Frontiers 4 opportunity announcement, and the science objectives, which I'll get to in a minute, we felt that those flybys of multiples and rendezvous were probably not the best return. So we decided to go with a high scientific target, and that meant either Carliclo or Chiron. And we went with this one, I think, mostly because of those pretty rings. There's something to be learned about these rings. Okay, so it's out there a ways in the outer solar system. It's also inclined 23.4 degrees. So, okay. Stepping back a little bit, the science governs the mission design. So what were the things that we want to discover? And in Vision and Voyages priority questions, there are 10 fundamental questions. 4 of these, questions 1, 3, 4, and 10 of that document, are what we decide to go on. So the initial stages, conditions, and process of solar system formation. What governed the increase in supply of water, chemistry, and et cetera throughout the solar system? What were the primordial sources of organic matter, and where does that organic synthesis continue today? We've heard a lot about that already. And how are the myriad chemical and physical processes shape the solar system, operated, interacted, and evolved over time? So these are what we wanted to address. And we did that by looking at a couple of goals. First one, the scientific goal, which addresses Vision and Voyages question 1, 4, and 10, which I just mentioned. Determine if exogenic processes dominate the current geological state of Centaur surfaces. Okay, and we have 2 objectives from that, and you can read those. They're also in our paper. But basically, what's the surface of the Centaur? Is it more like Phoebe, which is thought to be a captured Centaur? Is it like Ceres, Pluto, Chiron, or Comet? So we want to look at various ices and minerals. And then the objective 1.2, colors of Centaurs. How did that come about? Because we know that there's that color variation. Okay. Science goal 2, this is really covering a lot about rings and coma and things like that. So where are the rings from? Are they from previous outbursts? Although we've heard discussion that maybe that's not quite possible to do. Is it material ejected through an impact? Are these something that's been there all along? Okay. In the case of Carliclo, there are 2 rings and there's a gap between them. Are there shepherd moons involved? Okay. And of course, these physical properties of the rings. Okay. And the last one, science goal 3, is to characterize the surface and subsurface chemistry to constrain the origin of Centaurs within the solar system. We've talked a lot about that already. We want to look at isotopic ratios, deuterium to hydrogen, oxygen, nitrogen, some of the noble gases, which we found out we probably could do with our impact. Now, that leads us to instrument design. So once the science is figured out, and then we can get into instrument design. So we're flying this gigantic telescope, essentially. Okay, and this is dominated by the CAMUS right here. It's a visible IR imager, 300 to 900 nanometers coverage in the visible, and 0.9 to 5 microns in the IR. Okay, Heritage was a deep impact. So what we had to do is draw instruments that had been flown before. That's why there's Heritage listed on all these. We have an ultraviolet spectrometer, which was based on New Horizons ALICE, would probably be upgraded to Europa UVIS if this would proceed forward. We have a radio science experiment, which has an ultra-stable oscillator, and that was the Circe. SMART is our sub-millimeter. So we're looking at this through a lot of different wavelengths. Heritage is Rosetta. And then finally, the impactor, the bomb. It's a inert tungsten impactor of 100 kilograms, impacting at around 10 kilometers per second. We want to dig a hole and then look at the ejecta that comes off of this. There we go. So back to the mission design. We launched in Earth around early September 2026. We make a Venus flyby in 2027. Later that year, we go to Earth flyby 1, then another Earth flyby 2 in 2029. And then finally, we reach Jupiter in October of 2031. That maneuver lifts us out of the plane of the ecliptic on our way to Carliclo, and we get there in 2039. As we're getting closer in, we start doing a hazard assessment in early September of 2038. We're looking for, are there other rings? Are there other moons? Is there anything that we're going to run into potentially? And then shortly before we get there on New Year's Day 2039, we do a small burn and we release our impactor. It's non-guided. It's basically aim and shoot that cannonball. And then we make the counter on January 6, 2039. The impactor hits around the same time. And then after that, we do like we did with New Horizons. We send the data back over a period of a year, and the data science return goes to early January 2040. Okay. Encounter timeline, the real event. So at 195,000 kilometers away, a lot of our instruments turn on. This is encounter at minus 5.8 hours. We're looking at CAMUS, SMART, Circe, and COEUS, the UV spectrometer. They're all on. And the lighter colors are for the baseline science observation. That is the science that we want to get. This is what we're targeting. Threshold is the minimum science that we can get and consider it a success. That's in the darker colors. So you can see most of the instruments are on for pretty much the whole time. We start doing full global imaging around minus 5.8 hours. Full system thermal maps starting at minus 3.6 hours. The impactor occurs at minus 2.1 hours from encounter, and then we look at the plume that's coming off of this. Encounter at E0, we do some radio science. We're doing UV ring observations, similar to what Voyager did at Neptune, and then we're spinning the spacecraft around at E plus 42 minutes. We're doing back imaging. We're continuing to observe the ejecta plume. We expect the ejecta to reach out to the rings, as a matter of fact, and then after 5.8 hours, end of primary science, and we start just continuing to observe, if we can, and transmitting the data back home. So spacecraft design. This is another thing that you have to do when you go through these type of things, is you've got your instrument, you got your science, how are you going to put it all together? Well, in this case, power. We're in the outer solar system. Solar panels were too darn heavy, too large of a area to use, so we went with 3 MMRTGs, giving us 210 watts at 18 AU. And we have 8 kilowatt hour secondary batteries. Propulsion is standard workhorse type of stuff, monopropellant chemical thrusters, total delta V capabilities, you can see is 400 meters per second. That we have a monopropellant, standard off the shelf parts, nothing new there. Attitude control, pretty much the same type of things, reaction wheels, and then our command and data handling, 65 gigabytes of data is expected from the encounter, which we'll be transmitting over a period of a year back home. Total wet mass launch there is 913 kilograms. This is all capable of being done on an Atlas V 401. Okay. And then I'm going to leave it here so we can talk a little bit more, but I wanted to mention the acknowledgments. Our team was very indebted to Charles Budney, Leslie Lowe's, Carl Mitchell, Al Nash, and Joyce. And then I'm representing 17 other people who worked very hard and had a lot of fun putting this together. Okay.
Thank you. Okay. All right, I'm going to try this.
Long haul. Oh! First one of the day.
Oh, okay.
That's an impactor that missed.
At least 2 questions, but I will make just one for the time. You mentioned at the first or second slide about possible comet perihelion. Can you elaborate from where that idea is coming? You said something like possible comet perihelion. Yeah, that one. Yeah.
Here?
Yeah.
Oh, okay.
What?
The thought might be that maybe there's some outgassing that might occur on this one, but it really doesn't matter because we're not going to be approaching it at perihelion anyway. We really don't expect any coma, but maybe there has been some coma activity in the past. Maybe that seeded the rings. We don't know.
Yeah, because I think the lower limits, the limits from radio detections is very constraining. So I don't know if you can even detect something fainter than that. There is some old paper from, I don't remember the year, but there is some paper where they were looking for CO and there is nothing there. So it's one of the plots that were shown before in the morning is one of the lower points for Chaliklus. So I don't know why you will expect to find anything.
Well, okay. We're going to be there, and we've never gotten this close before, so we're thinking maybe there might be some small outgassing that we wouldn't be visible from Earth or Earth orbit.
Yeah, I'm dubious about the levels that you can detect on site will be not very constrained in respect to what we already know. It's just that, yeah, okay.
Okay. I couldn't hear you.
No, I'm not going to risk it. Here you go.
Maybe I missed it, but what was the cost cap for this?
$850 million.
So is that a New Frontiers kind of
That's
mission?
a New Frontiers, okay. Correct. That brings up a good point, and I forgot to mention this. They threw us a monkey wrench on Tuesday of the week that we were at JPL. They said, you guys are doing really great. You've downscoped your instruments. You haven't been fighting or bickering over that, which is rare. And they said, okay, now you're going to do it under discovery cost cap. With a little bit of tweaking, this mission, with a little bit of downscoping of science and a little bit of tweaking on the number of MMRTGs, this could be done under discovery. close. But yeah, it was definitely under New Frontiers. So on Wednesday, they let us go back to New Frontiers, and it felt like a bargain. I mean, it felt like a lot of money was given to us at that point.
All right. So Jordan Steckloff, PSI. So this is really fascinating. Could you go back to the slide where you have the trajectory and the flybys?
Yeah, it's a little bit forward here.
Yeah. I got a little hung up. So it looks like these Earth flybys and the Venus flybys, like added all together, you're getting just a handful of meters per second over several years of mission time. Would it be just possible to use those mission funds and instead strap an extra booster on the rocket and get that same delta V?
I think when we did this, I think there was some options of using a heavier lift vehicle. I do not recall why this was the way we decided to do it. Honestly, this was decided even before most of us got to GPL. So I'd have to dig into it or send you to Sam, and maybe he could tell you a little bit more.
Okay. We have time for one more question.
Really?
Okay.
Yeah. Ask away. I mean,
I can ask later.
Yeah.
I will not raise another. You mentioned in the concept you were looking for more rings. Can you elaborate what is the nature of the experiment to detect more rings?
Well, it's
that
not
cannot
that
be done from the ground, for example.
It's not that we're necessarily looking for more rings, although that's always a possibility. If you remember when Voyager went by, ring arcs were discovered at Neptune. So the possibility is if we've got rings and the occultation studies show that there's already 2 rings with this tiny gap in between, that's probably telling us there could be shepherd moons involved. There could be there could be objects in the way of our spacecraft. That's why we want to look carefully. But of course, if there's not, we still want to keep looking at the rings because that's part of the science. We want to see.
Okay, but the specific ways with occultation from the spacecraft, that is the experiment? I mean,
yeah, actually, when we come behind, so imagine we're going behind now, we can look back towards the sun.
Forward scattering?
Yeah, and we can actually look in UV, we can look through visible IR, the radio.
Did you work the numbers of how faint can you go? Because with occultation from the ground, you can go very faint. And there are already some good constraints of extra rings. I think in 2017, I was looking at the paper to look at the numbers, but the Amber R was working in the same group, and there are some strong constraints. Maybe you know how deep you can go.
Yeah, typical Alan Stern, Southwest Research, typical ground-based occultations can get you down to like 10 to the -3 or 10 to the -4 optical depth. But in forward scattering for reasonable phase laws, you can get down to levels like 10 to the -8 for your I over F. So you can do much more sensitive job.
Yeah. It's okay. Thanks, Alan. All right, Sean, thank you. Let's thank our speaker one more time. And our next speaker is Walt Harris. You go by Walt or Walter?
Yes, sir.
All right.
James.
All right, great. So Walt is going to talk about volatile activity and encounter missions with Centaurs. And all set? Great.
So, well, until we had an additional talk at the end, I was going to be the final version of this, and so I thought I would have a little bit of fun with everything that we had said and start talking about what we all really want to do, which is stop observing these things from the ground and go somewhere. I also knew that there was absolutely no chance that any of the things that I was going to show would not already have been shown 3 or 4 times in this conference. So I figured I would focus primarily on using what we have and let me clip this in here.
Yep, sorry about that.
Yep. Focus on what we do have in terms of information and how we want to explore some options for going somewhere. And I've given us our fanciful idea of what this might look like. I have stolen the Lucy spacecraft and diverted it to a moon of Saturn that I have attached a jet from 67P to. But you should imagine this as a Centaur mission, okay? All right, so to start with, we have our obligatory things that we all know that I have to say at the beginning. We have a family tree of icy planetesimals that include the Oort cloud and the Kuiper belt objects that are in long-term stable orbits. We have the evolved population in the Centaurs that are a long-term stable orbit. And then we have long period comets, which are extremely hard to visit, but relatively pristine, and short period comets, which are not very stable and short-lived. And in between, we have the Centaurs. This is why we want to go to these objects. And in addition, as we've been talking about all along, the Centaurs are this orbitally evolving population that is going into the Jupiter family. But it's important when you think about this process to understand that this is not a straight arrow from here to here. It's a wash cycle on high for orbital stability and dynamics. So it makes it very difficult to use the Centaurs linearly on an individual basis as something that we can identify processes on. So right now, our current state of understanding of icy planetesimals is dominated by the things we can get to, and that's the Jupiter family. And the Jupiter family objects, as I already pointed out, and we now see, are very highly evolved compared with their stable parent populations. Could argue the long period comets are significantly less evolved, but given the stochastic nature of their appearances, their high inclinations, and their high velocities in the inner solar system, going to them is a lot harder. It might even be easier to go to the Centaurs than to a long period comet, at least for any period of time. So our task with the JFCs is to invert their modern state back to the Kuiper belt. And that has been very difficult up until now. But now that New Horizons has been to a Kuiper belt object, we now understand the scale of the task that we have to address. We have to somehow get from this to this. And when you put these things in context with each other, it is very obvious how not primordial the Jupiter family comets are. If you were to take this thing and blur it out to 75 meters per pixel, it would still look more evolved than MU69. So it's very clear that there are a number of processes eroding these bodies. How much of the mass of 67P is gone from what came into the inner solar system, we don't know. And so this is what elevates the Centaurs to a target for study, and why we are all here, and why we spend time trying to detect gas production from these objects at 30 AU, because we understand this process. So the problem with getting to these that we've talked about in some of the discussions today is that they're a difficult population to use as an easy proxy for evolution. We assume that the Jupiter family and the Kuiper belt are the covers of a book describing the evolution of icy planetesimals. The problem is the Centaurs are the chapters, and someone has randomized the numbers on those chapters. Where a Centaur happens to be inside the solar system at any given time between Jupiter and Neptune is not necessarily an indication of its evolutionary state, because it could kick back out or back in. And this is shown in just sort of a sample of what happens when you forward model one of these things. Beyond a very short period of time, sorry. No, it's, sorry, that's nothing I can do about it. I'll show you, I'll send you the paper afterwards. Okay, anyway, my point isn't that this is a correct model, but it's fairly typical that if you want to explain these objects more than 1,000 years in the future, or even maybe a few hundred years in the future, it's a statistical game. You can't guarantee in this particular case whether this object has gone all the way into the inner solar system or practically been kicked back out of the solar system. All of those are potential outcomes. And so it becomes very hard to determine the state of any object with distance. And so if you look at one of these objects and it's more or less active than another, you don't really know if that's because one is younger or newer than the other based on its dynamical history alone. So that brings us to the subset of objects that we know are not finished evolving and at least have started evolving. And those are the active centaurs. We may not know any of their dynamical ages, but we know that they are undergoing some kind of structural modification relative to their previous history in the Kuiper Belt. What that process is not very well understood. So it's these objects that we can go to and see where and how that evolution is happening. We can also go to the inactive centaurs, but we don't know before we get there whether they have actually started evolving or whether they have already been in the inner solar system and kicked back out and are finished evolving. We don't know anything about their state. And the lack of activity takes away our opportunity to tie activity patterns we can observe to features on the surface so that we can see how those processes are playing out. So as we've already pointed out multiple times, 10 to 20% of these objects, so somewhere in the neighborhood of 50 to 60 centaurs, are known to be active. And this activity, in addition to being important for understanding the evolution, is arguably incredibly interesting and important taken on its own merit, because it isn't the same activity that we have happening in the inner solar system. From Gerbs' 2015 paper, you can see that activity in long period comets beyond about 4 AU follows an entirely different, all but flat activity pattern with heliocentric distance. And we have one Centaur on here, which Gerbs put in as a Jupiter family comet. But you can see it falls right along this line. This outer solar system population is evolving in a fundamentally different way, which means also that there's no guarantee that the evolution patterns we'll see on these objects are going to directly tie to the evolution patterns we see on the Jupiter family comets, which are sublimating by a different process involving water. So clearly they don't have much of a heliocentric dependence. And in fact, outbursts in activity can occur on all heliocentric scales of an orbit. I first saw this figure earlier today, and I think it's really important. It's interesting that the active centaurs do seem to be clustered into groups of objects that are in orbits that are controlled primarily by Jupiter and Saturn that may represent some hint of an evolutionary track that these objects are following, but it could just as easily be that they are harder to observe for activity patterns when they are farther from the sun. So it's possible that there are more objects in this grouping out here that are active at levels that we don't understand. We can also see that the activity, when we take it as Maria did and Olga, yes, sorry, and put in here, when you put everything on a panel, this you can see is Hale-Bopp right here. So there is some indication that the Centaurs follow a Hale-Bopp-like activity pattern, at least the Hale-Bopp activity pattern as they were coming out. So it does indicate that maybe the activity that is coming from the Centaurs is closer to primordial. It's not clear that if you took the Jupiter family and shoved them out into the Centaur region that they would be active in the same way. That may no longer be possible for those objects. But the point is, there are a tremendous number of biases attached to this. That is, observational biases, being able to detect activity, which objects are close, which objects are not. It's really a crapshoot to try to pick things based on guesses about their observational state. So my position would be that we should just simply target something that's going to give us a good opportunity to look at activity. And also, simply from an accessibility standpoint, the objects probably in this group are also the easiest for us to get to. And then, of course, there's the other thing. Centaurs have outbursts. The outbursts are just like the rest of the activity. It doesn't happen just at perihelion. The largest outburst ever recorded on Echeclus, for example, the one that looks like it's split into two objects, did not happen anywhere near perihelion. It was at large heliocentric distances. And then, of course, there's 29P, which outbursts all the time, and we don't know why. If it's an object that is the only object in the entire solar system that repetitively outbursts on a predictable cadence. As Jordan refers to it, it is cold faithful. Well done, sir. So we don't know what mechanisms are driving that activity. All right, so what does all of this mean for an encounter? Well, I would contend that if our goals are to understand the intrinsic evolution of these objects and how they bridge between these two populations, we should target the active population. But there are real challenges to doing this. SW1 is the only Centaur that is known unambiguously to be active on all time scales. There are activity patterns from several other Centaurs that may be continuous, but may not. In other words, there's sporadic activity from several, like Echeclus, and then other times we don't see it. That doesn't mean it's not there necessarily. It could mean that it's just below our detection limit, because our detection limit is so close to the edge of what we can see. It's also true that the outbursts and activity do produce debris that we can see stably surviving around these objects. So that produces a complex environment that's not terribly easy to get to. And the last thing is, of course, we're going to the outer solar system, to small bodies, which is a technical challenge if we're going to explore them. All right, so I'm going to just throw out there so we can start talking about it, 3 ways that we can try to do exploration of these objects that, that have pluses and minuses. And there's something that we can discuss as a group. The first is to have orbital encounters. The second is to do multi-object fast flybys, by which I mean you do a tour, grand tour of objects, and you don't worry about being ridiculously close, but you go quickly past each one of them. Or you try to target one for as close an encounter as you can possibly get, not necessarily being able to get into orbit, but being able to get into the vicinity for long enough to actually characterize some of the things that are happening around it. They all have pluses and minuses. Orbital exploration is, well, everyone would like to have an orbital mission. If you compare the flybys of the Jupiter family, add them together and say you can have those or you can have Rosetta. Rosetta is going to probably win. And that's a great way to study one of these objects in detail. Timing of sporadic activity ceases to be a problem if you go to one of these. The outbursts now, as opposed to being something you're scared of flying through, are something that you can just sit and look at. Spacecraft can map everything in detail, and you're not moving very fast at all in your orbit, so you don't have to worry about hitting anything. The drawback is it's really hard to do this. So in the 213 decadal survey, there was a concept study to try to go to Chiron. They looked at Chiron, Echeclus, and Okoroe. If you know anything about orbital dynamics and mission requirements, I can tell you those are bad numbers for a cheap mission. So they concluded that we needed new frontiers or flagship class missions with nuclear power. Now, there are orbit solutions that you can optimize to get to some bodies easier. Maybe you save some energy. Maybe there's a keyhole you can get through. You can do something great. But for the most part, those things are few and far between because orbital phasing is unlike in the inner solar system where you can go to Mars every 2 years. You might be able to go to Echeclus every 50 years because Kepler makes things go slow in the outer solar system. So probably a more likely solution is to do a series of fast flybys of several models or several objects as kind of the standard flyby model that we've been using in the Jupiter family. There are far more trajectories available. If you can find a trajectory that targets multiple Centaurs, which you could do if, say, you stay in the plane of the ecliptic and you go to ecliptic crossing points for multiple Centaurs, you can reach several of them in relatively short timescales, still 10 to 15 years probably, but you can still do it. This comes at it also allows you to deliver a slightly more capable experiment for the money, or you can do it cheaper. The risk of missing the activity is going to be ameliorated by the fact that you fly by more than one object. So you have a shot at doing that. The downside of this, and I'll just go through this very quickly, is it's a dangerous thing to do to fly by these objects at this velocity. We've flown by Ville 2, Hartley 2, Temple 1, and you can see the size of the hill sphere of these objects. They're small. And these numbers are, for the most part, smaller than the distance that the spacecraft traveled in the vicinity of these objects. When you get out to Schwarzmann-Lachmann 1, it's 20,000 kilometers away before you're out of the hill sphere. If you go out to Chiron, it's 100,000. If you go out to Cariclo, it's 230,000 kilometers away before you are outside the region where debris could be caught in a permanent orbit. That's a little scary. Now, I'm not worried about being 230,000 kilometers away necessarily, but it does mean that you have to be very judicious in your decision about where you're going to go with respect to debris. Also, they come with the other limitations, which is that you have less coverage of features, activity patterns, rotation, et cetera, and less time to adapt to unexpected activity like an outburst. Which leads me to the third kind, which is what I call a drift-by encounter. And for this, I think is a middle ground. In other words, you tailor your encounter using phased orbital trajectories so that you can get to an object with a very low relative velocity, say under 1 kilometer per second would be ideal. This has some of the advantages that you can get to these objects without having to match all of the orbital elements, eccentricity, argument of perihelion, inclination. There are more opportunities at lower cost. You can deliver more instruments, and you're better able to respond to activity because you're slower as you're coming in. It also allows for closer approaches because your relative velocity is lower. The downside are pretty much the same, which is you don't get a lack of, or you don't get to compare multiple objects. You just target one a little more deeply. You have lower velocities. You may get a closer approach, but you still are threatened by particles. So you can't go in to like 200 kilometers from 29P at 1 kilometer per second. That's just not going to work. You may get more time in the vicinity of a target than a flyby, but still much less than an orbit. There are a lot of things you can't do that you could do with even the most basic orbital mission. But it is a way to get a more detailed look at one object. So I know I ran over on this, but just to put up my conclusions is what I just said, but this leads to the questions that drive which of these types of missions you want to invest our energy in as a group to pursue. What's our highest priority for the exploration? How do we maximize our chances of getting a mission selected in the near term? And what should the targets be of that mission?
So I don't think we have.
Yeah.
We
so
don't
I actually think that these are good questions for the general discussion we have either later or tomorrow. And
can we ask questions about thought?
Sorry?
Can we ask questions about thought?
Tomorrow? Tomorrow? You mean, or
no.
Tonight? Right now?
Yeah, questions. Yeah.
It's 4:40. I think that's the next.
You can take it out of my time.
He's the next speaker. So no. Please.
Yeah, I have two questions. First, has this drift thing ever been done before? And second, can you get a drift from all the studies you've done? Can you get a mission design that'll get you to multiple objects at slow speeds within the constraints of discovery?
The answer is I don't think it has been done before. in terms of just, I mean, usually when we're targeting the Jupiter family, we don't, it probably could have been done. But I think in the case of the Jupiter family, if you can do a drift, you probably have the delta V to do an orbit. And the problem with these is that because the timing between when you can do that is so far apart, most of the time what you can do is you can get really achingly close, but not quite able to get all of the parameters of the orbit matched. And so while you get there with a kilometer per second of delta V, normally you would say, then just burn another kilometer per second of delta V, except that's enough to push you into a new frontiers. Unless you have an ion drive that somehow runs on, that's free, yes, that draws its power from the ether. It would be great if we had that. But as for getting to something else, I think in fact you could come up with trajectories for it. And it would depend on what you did. If you targeted one of these for at the right time, you could phase it to another object, say in a similar inclination, and maybe catch that one if you pick the beat pattern of those closely enough. I think it could be done.
Great. Let's thank the speaker. Are you ready, Alan? Okay, great. Our final speaker for the session will be Alan Stern from Southwest Research Institute.
Oh, sorry. The slides though, right? And this is great. Okay, great. How about half the lights down because there's good eye candy? Just about like we had for Walt. Okay, let me thank Gal in particular, but the organizers in general for inviting this walk-on talk. The only thing I didn't know when I agreed to it was that I would be the only thing between you and a break with food. But nonetheless, what I want to do is kind of walk a fine line. I know everybody here has seen some of the results from this spectacular body that we flew by with New Horizons on the 1st of January. And those of you who are going to LPSC are going to see 30 times this amount of material because we're giving over 24 talks on Monday of LPSC and some posters as well. And further, I have an agreement with NASA that I can't release any more than has been publicly released until LPSC. So I can't tell you new things today, but I can put it all together in one package. And when we take the break, one of the co-investigators on this mission is Kelsey. And she'll be available for questions too, I'm sure. There's one thing that was released today that didn't make it in this talk because it just got released 2 hours ago, which is a cool stereo product. And I don't have 30 of these, although at LPSC we will have 300 for the room. But I have one, my own, and anybody that wants to see it on my machine can see it at the break or tomorrow. Great, okay. So anyway, let's jump in. So New Horizons was famously to be the first exploration of the Pluto system. And that turned out very well. But the reason that mission got funded is because the first decadal survey, the 2003 decadal survey, recognized the importance of the other dwarf planets in our solar system and the context of the Kuiper Belt, and actually recommended this mission, not calling it Pluto mission, but calling it Kuiper Belt Pluto mission, emphasizing the exploration of the Kuiper Belt, and required that the mission be a package that included the flyby of at least one small KBO. And then all the teams that competed had to design a spacecraft that could go on, had the power, the comm, the fuel, the longevity, instruments that could work in lower lighting levels further out, all of that. And so that's what we're doing now. We finished our prime mission after downlinking all the Pluto data in third quarter of 2016, a year after the flyby, a little over a year after the flyby. And then having found suitable targets with the Hubble Space Telescope, we chose one. We chose the closest one because it minimized risk, and this one also minimized the fuel expenditure required so that we had the most amount of fuel to attempt to get to a second one, which is our hope. And so we've been out in the Kuiper Belt since the Pluto flyby for 3.5 years. We've flown about 1 billion miles, 10 astronomical units, on to this spectacular object that I'll show you about. At a very high level, not a scientific level, but at the press kit level, these are the scientific objectives for the mission. And this is not only the most distant and primitive object ever explored, because this is, by the way, not a scattered belt object. It is a cold classical. And if you don't know anything about the cold classicals, they're not called cold classicals because they're freezing cold. They are, but it's because dynamically, the orbits are cold, low eccentricity, low inclination, and they are essentially the equivalent of what a Martian geologist would call a bedrock sample of the nebula at this distance. This is a population, unlike the scattered disk, that was not brought out and embedded to this distance by scattering off giant planets. It was formed in situ right here. And in addition, this is the first small body at large heliocentric distances that we've ever explored up close that's not been associated with a planet. So this is the first heliocentrically formed object like that we guarantee know its history. This is a cold classical. It came from right here where we saw it in the flyby. And our objectives were geological mapping, composition mapping, search for an atmosphere, which we didn't expect, but you got to look. Certainly would be headlines if we found it. Satellites and rings, and maybe satellites are a little more likely. In the cold classical population, we already have a 30% detection rate among satellites, objects with satellites. And in fact, we know that's a lower limit because of selection effects. Okay, I want to show you a short little video. I might have to go over here and start it. So this is a, whoops, oh, yeah, that can make it work. This is just a zoom up on Pluto. Whoops, let's see if I can do that. Right there, from New Horizons images. Hopefully it will start. Oh, is that right? God, I can show it to you. It's great. It's too bad.
I saw it. It's pretty cool. I think it's frozen.
Okay, so I'm not going to be able to do it, but I'll tell you what it does. It just takes these gorgeous images of Pluto and it zooms up on the nitrogen glacier, Sputnik, right to about here, and then it puts Ultima Thule for context. And you know the difference between a planet and a planetesimal when you see that video, and Kelsey and I can share it with you after. So what we were flying up to was something the size of a single mountain block on Pluto. Continuing, whoops, I don't want to do that just yet. There. Okay, this is our first resolved image. We called it a bowling pin. We had pretty good hints, as you've heard before earlier in this meeting, from Mark Bowie's occultation, that we had either a very closely orbiting binary or a contact binary. Even at only one day before the flyby, we still couldn't tell, but we could certainly tell we were going to have something interesting. And here's a candid shot from in our geology and geophysics room. At the time, the very first high-resolution image came up for everybody to see. Is it Kelsey? Is that you? Who's that?
I'm not sure.
Okay. Okay. Well, but there's Simon and there's Jeff and there's other people. There's Ann and there's Todd. Okay. Anyway, this is what it feels like to really be at the moment of discovery, right? And this is completely live and completely candid. Okay. So let's turn to scientific results very quickly because there is a break coming. We found no evidence for coma or atmosphere. No surprise. We have very sensitive limits from both air glow and ultraviolet A-pulses, where the line of sight got very close to the target looking at bright ultraviolet stars. No evidence for rings in either forward or backscatter with very sensitive limits. In fact, not only not rings, dust structures of any kind. No evidence of any heliospheric interaction from our plasma instruments. We did see that with Pluto, but Pluto's the size roughly of the United States, and we flew by about as close as Tokyo to the United States. In this case, we flew by something the size of greater metropolitan Washington, D.C. at the distance of Los Angeles, and it's just too small a body to create effects at that distance. We had modeled this, we didn't expect an interaction, and we didn't find it. We also haven't found any satellites. It's too bad because a lot of these cold classicals do have satellites, and that would have been a bonus. But the object that we did find, I'm having clicker problems, is spectacular in and of itself. And this is one of the first images to come back, so it was not particularly high resolution. Walt showed a very nice image at the beginning of his talk that put this to scale with Comet CG, which would be maybe like that on this scale. This is an object that's 6-7 times bigger in major dimension and is of order many hundreds of times more massive. It is a contact binary, which actually means that it used to have a satellite, which have now merged. On approach, we couldn't find a light curve. We figured out why at the very end. Here's some approach images that start off fuzzy. And what we've done is we've adjusted the size to be identical because it's easier to see. So it's fuzzy and then it's getting sharper. And essentially the pole vector is back towards the sun in the direction that we're coming from. And that prevents you from finding a light curve. Now, the interesting thing about this is a clue also about the origin, because a lot of formation models, including some brands of what would be called pebble cloud collapse, would predict that the pole should not have a 98-degree obliquity, but should be straight up and down relative to the plane of the nebula, or completely upside down, depending on how you do it. So this, we think, is going to help rule out some models. We have color data, but I can tell you we don't see very much color heterogeneity. That's the color image. The color imager is lower resolution than the panchromatic imager. That's the panchromatic image in the middle, and then the color draped on top of the panchromatic on the right. Now, we have much better products than this that we'll show at LPSC, and I can say qualitatively, when I say little color heterogeneity, it doesn't mean zero, and we'll have specifics for you a week from Monday on the 18th. As to the spectrum, start on the left and you see a few sparse dots. Those are the color filters of our color camera. And you see the red slope. It's about 21% per 1,000 angstroms. And then you see the slope bends over in the infrared. Our infrared mapping spectrometer has hundreds of spectral channels, so much denser spectral coverage than the filter camera. It goes out to about 2.5 microns. And the very first detections, which we've already announced, are detections of water ice band and a tentative detection of methanol. We'll have more to say about that too. I can also tell you that the two lobes are virtually identical in color and in their infrared reflectance slope. Here is a close-up of a much better image of MU69 than anything I've shown you so far in this talk. There's some things, we've already talked about it being a pristine cold classical, 35 kilometers in length and being a contact binary, but everything we can see in its geology indicates a gentle merger. In fact, some of the geology folks even call it a docking, but that doesn't sound right to me because it sounds like, you know, there were pilots involved. But we can't find any evidence of a high-speed impact. This suggests that the two objects were formed together in a local collapse cloud. By the way, yesterday, this new Sarah Greenstreet paper was mentioned, the 2019 paper. And I think Kelsey said the typical impact speeds on cold classicals are about 300 meters per second. If these two things had run into each other at 300 meters per second, you would not get this result. They would be shattered and probably a debris cloud out in the Kuiper belt. This had to have happened at speeds more or less like their mutual gravitational collapse speed, which is measured literally in meters per second. We don't find stress fractures or any other telltales of a higher speed collision. So the binary, which was orbiting, hardened through the loss of angular momentum, probably by ejecting other things out of the collapse cloud until the two merged. Now, did they merge once, or did they merge several times and bounce? And this took place over some, who knows, tens or hundreds or thousands of orbits that it finally settled. There are people on our team that think they see former low-speed collision zones on the larger lobe. And by the way, I think I got the terminology slide out of order. I just wanted to say, we got this name Ultima Thule, that means beyond the farthest frontiers, from a web contest we did. The public suggested it, the public voted up names. This was the one that was near the top. And what we picked, we liked the meme that was involved. As soon as we saw it was really a contact binary and there are two objects there, not being very original, and we had to name them overnight, we just decided the big one would be Ultima and the little one would be Thule. And the other thing that of course pops out right from the beginning is right at the merger zone, there's this much brighter collar or neck of material. It's not the only bright material. You can see that for yourself here, but it definitely stands out. I think it's the most remarkable albedo feature on the surface. Now, the entire object has an average albedo of 7%. And although we get very low albedos down near the terminator, that's really just a geometric effect. So if you exclude the pixels near the terminator, everything you're seeing, including the brightest stuff, like at the neck, only ranges from about 5 to 15%. So everything's dark here. Even the stuff that looks bright is not bright like on Pluto's surface, where you can get near unit albedo. It's just relatively bright. Here's just a pair of time lapse. You can see it rotating, but I want to particularly point out, do I have a laser in here? Oh, the black, right here. Okay, take a look. There are a bunch of units on the surface. Like here's probably the best one. It's almost circular, but there are others. They are roughly like-sized. There are of order 10 of them, 8 or 10. They're not only like-sized, they abut one another, and typically at with a border where they abut that's got a higher albedo than the centers of those units. Is this a result of something that happened on Ultima? We don't see that on Thule, the other lobe, because of its larger size, and it trapped more radioactive products earlier, perhaps. Couldn't be much earlier, we think. Or could they be accretional subunits and this is some hints about what was going on in that local cloud collapse. People are going to work on this for a long time. We haven't done any serious modeling yet. When you're part of the New Horizons team after a flyby, you feel like a doc in an ER. You're just triaging patients as they land on the ground, new data sets every week. Now, let's talk about the shape. As we got images from various angles, we began to see that the object looked like it wasn't what we expected, which was more or less spherically symmetric, that it looked distinctly flattened. And you can see it just in these two images alone, that the Ultima lobe looks more like a disc or a coin. And the Thule lobe itself also has some of that. Maybe it's more like a walnut. Oh, I have to show this image. Okay. So here's the departure image that kind of clinches the case. I sure hope that worked. So we actually had the idea as we planned the flyby that we would look back at very high phase angle and try to recover shape information. We thought, well, if it has a satellite, it'll cast moonlight and that'll work. And if it doesn't have a satellite, we'll watch which stars in this star field wink in and out and get a shape profile that we otherwise wouldn't have to add to the entire database of what we can learn. I should have put it in loop. Let's do it again. There it goes. It's undeniably flattened. And the end result or the end preliminary result, not final result, is that shape model. And this is what's key, okay? This is looking down the barrel like that, actually from the other direction. And then here you see it from the side, and they are very unusually shaped objects compared to your instinct or what you would think would happen in a spherical cow model of cloud collapse. Is this a telltale of angular momentum, of collisional history, of something else? We don't know, but I can guarantee you this is going to be a lot of food for thought for theorists. And if these are common in the Kuiper belt, this kind of shape, then that's going to be very important. If we just happen to run upon an oddball, then we did, and we saw maybe an extreme kind of accretion and merger event in some respect. We can know that. We can know that because we've got the capability now to do additional stellar occultation profiles with the techniques that Mark Bowie developed. He didn't just get Ultima once. He got it 3 times in 2017 and 18 combined. Showed he could do this repeatedly. Get under the shadow of an object that's a milli-arc second across. And now we can go out and look at other cold classicals. And if we go do this 6 or 8 times and they all look like, or mostly look like contact binaries, that's going to tell us one thing. And if we can't find another that matches it, that's the other end of the spectrum. So we don't have to do very many to start to understand whether this is typical. Now, we've had other things happen in planetary science where first flyby of a new object type, first flyby of an asteroid revealed a satellite. And we know they're virtually ubiquitous in the main belt. So this may be telling us that this is the norm, and that all the objects that formed with the cold classicals actually out there at 44 AU were forming in these local collapse eddies, and that they, the details of the process produce very non-spherical cows. And this is, I think, my last slide. I already said come to LPSC. We have 40 talks and posters. Most of them on the Monday, the very first day of the meeting, but some are scattered throughout the week. We have submitted our first paper to Science, and on Wednesday, got the referees' reports back. And we will submit, and I hope that that paper is on the cover in May. We're working really fast to get back with a response to the referees. We've got a set of 3 papers that will be submitted together, one on geology and geophysics. John Spencer is leading, one on color and composition that Will Grundy is leading, and one on the origin of Ultima Thule, and Bill McKinnon is leading that one. And they'll all be submitted approximately May 1st to 10th. And then we hope they'll be published in August or September, depending upon the refereeing cycle. We also have an Icarus special issue that anyone can contribute to. You don't have to be New Horizons. And it's got a September 15th due date. So look for that. And if you're already interested in doing some modeling, for example, have at it. And I think that really is my last slide. Yeah. Okay. Thank you.
All right. As long as it's okay for people to delay the break for about 5 to 10 minutes for questions. Is that all right with this crowd?
Yeah.
All right. Okay. I couldn't figure out who went first. So.
I'm sorry to speak for everybody. Okay, Jordan Steckloff, PSI. So, wow. So many different questions. I guess we'll just start. The neck, the collar. So yeah. That looks very ubiquitous that we see on Jupiter family comets. Obviously, this is almost like a naked one. And so it also looks like a lot of these higher albedo features are in depositional areas. Is that correct? Are these topographic lows or places where you'd expect material to collect?
The neck certainly is. The neck is obviously, at the neck. But by the way, I didn't say this, but you'll notice there are different types of bright features. There are what we call linear and curvilinear, and you can see a lot of them on Ultima, the larger lobe. There are also very distinct bright spots. There are also some circular ones up there. And then there are some bright patches or zones like here. And I could point you to several others. But The bottom line to this is we don't have the resolution in the available DEM yet to establish your hypothesis. Okay? Certainly at the neck, we know that that's up at a place where things should collect.
Okay.
What is the albedo difference between those?
Factors of 2 or 3 between the darkest and the brightest stuff you see.
Walt Harris, University of Arizona. Alan, I look at your rotational axis, and I wonder how detailed your volume estimates are for Ultima and Thule, because it looks like Thule is maybe slightly more massive than Ultima and maybe denser.
We'll see. I can tell you the shape model's still in flux, not at the basics that it's flattened, but the details of it.
Well, I'm not even talking about the basics of the flattening. It's just that you can see from that picture they look obviously very different, but the axis is almost right through that neck point.
It's actually offset from the neck. And one of the things you should notice, I didn't point it out, but I will now, is that one of the interesting things about the shape of the overall body is not only are the 2 lobes individually flattened, but the principal axes, the 2 lobes, are virtually aligned, which tells us something about how it came to an equilibrium in that merger process.
I'll just say too that the way this pole is selected is based on the shape model.
Okay.
So if you look at some of the other images Alan was showing, the Ultima lobe doesn't look quite so pointy on the edges. It's actually a little fatter. Okay. So that will actually change. So it's actually tied into this and not a solution on its own, if you know what I mean. I assume that. Yeah. Okay.
And so it's got the error bars of the pole solution in it. It's got the error bars of the shape model in it. And it's got the assumption that the 2 lobes are identical in density and porosity.
Okay.
Right?
So given all of that, do we have a rough volume?
Oh, sorry. I earned this. Okay, I don't know. Is this part of the previous conversation?
Yeah, I was going to ask, so given all of those assumptions, what do we have, like, roughly, are they close to being equal volume, or is one significantly larger than the other? Can you say?
They're 0th order equal, and 1st order, let us do more work. Okay? A lot of things have changed more than once in the last 6 weeks because we're getting more and more data sets to the ground. We've got 20 months till we get all the data to the ground. So we're very early days still, although the highest priority data comes down first, and that includes the highest resolution imaging. But we have lots of approach imaging still to come that's going to help constrain the shape model, resolved shape imaging. And I should put in a plug for what Walt was talking about. I think that Ultima Thule is telling us that missions to Centaurs are going to be very worthwhile to do. And because they come from a completely different population, the scattered disk, this is not a repeat getting more cold classicals. Any kind of mission like Walt talked about, or like a mission to Chiron that I'm interested in, is going to be sampling a completely different formation environment, because the scattered disk objects were almost certainly formed down among the giant planets and then transported outward to cold storage.
Okay, Julie Brousset, FSI. I just wanted to say, so there is a model of KBO formation by Davidson 2016, where he predicts actually that larger KBOs, like 100 kilometer and up, are going to form as a cloud collapse. But under that, the remaining material will have, so there's like little material left, so they will have collision velocities under 10 kilometers, under a few tens of meters per second. So there are formation models that do predict that you could form these by just binary collisions of, from millimeter-sized grains all the way to a binary like this.
But in a local cloud.
So this would be, I don't know, so when you say local cloud, do you mean the one that collapses to form a body?
Yes. So you cannot have strong crossing velocities and produce objects like this. Because if you do have the strong crossing velocities like the Green Street model would give you, those are erosive collisions. They're 1,000 foot per second, like a bullet.
Yeah, so
So
Okay.
you had to have things in very neighboring orbits.
Yeah. So, yeah. So, but he just predicts 10 meters per second, and these are like remaining objects that were not that were leftovers from these clouds that collapsed. I'm just okay.
Thank you. Matthew Knight, University of Maryland. I'm just really interested from the light curve perspective that, going into this, looked like there was no amplitude, but had it been aligned, the spin axis has been aligned like D and E.
Right. If the pole had been pointing north-south and perpendicular to the original nebula, right, we would have seen something very different.
Yeah, like a 2-to-1 amplitude or something.
Yeah.
And you were saying, with asteroids, the first time we saw something turned out to be very widespread. Just speculating, maybe there's some preferential thing where we think stuff is quite round, but in fact, if we
actually have a paper that's hoping to go to Science next week that's not a part of either special issue that's related to what you're talking about.
Okay, great. I look forward to seeing
Mark Showalter's leading that.
All right.
All right. Thank you, Alan. I'm not going to try and do geophysics on a JPEG. We can wait for actual data. So a couple of comments. The first thing, as a modeler, I was very disappointed when this shape appeared because I thought this was going to be the perfect two little balls in the Kuiper belt, which are perfect for modeling, and it screwed up everything for me. So,
Think of how many successful grant proposals you can now write that you couldn't have written.
Right. So I think, without doing the geophysics on a JPEG, I think you've mentioned the possibility of what kind of processing history this object had. I thought about this, and not a lot, probably. It's probably one of the more pristine objects you can find. Well, obviously, it's very far. It's in the classical belt. Mm-hmm. But for its size, and specifically for the fact that it does look like two separate small objects that came together, the efficiency of radioactive heating to do anything in a body like that is extremely low. So whatever divots or neck regions, or things like that, I would venture to guess that they're probably connected to the origin of this,
to the
accretion process of this, and probably almost nothing else. That's a guess. That's not not even educated, just a guess.
Okay. Is there a question, or that's a good guess? I mean,
how does so it's a binary. It's a classical. It's a cold classical. How does that fit into? I think it was Wes Fraser's model backed up by observations of the color model. Yeah, the color model for the cold classicals.
This is a typical color.
So
the two lobes have the same color. I said that earlier.
Right.
Very little variation across their surface, but non-zero.
Mm.
Yeah.
I don't know if you can answer it.
If we can dim the lights, I'd like Kelsey to cover one point that I didn't cover, which this allows us to cover, which is, can we dim the lights halfway so you can see it better? Okay, take a look over on the Terminator side where you think you might be seeing craters, and you might be seeing craters. Where it's high sun on the right, you shouldn't expect to be seeing craters. But over here, where you have the shadows, right, Kelsey?
Yeah.
Craters? Impact craters? Yeah, this is a big crater, for example, we think. But anyway, you want to talk about whether these holes in the ground, what they might be?
Sure. I guess, should I get the question?
Do you want the laser or the microphone?
Thank you. Okay. Just briefly, this is part of what I'm looking at for LPSC, but just given the lighting and the resolution, should we be able to see craters? And if we don't see them, then they're not there. But the Terminator is nice because you do see a few examples of the morphology that we expect to see. Yeah, so if Alan points to the one that's closest to the neck on the little triplet.
Down here?
Nope, there you go. Yeah, down. Yeah. Anyways, there's even like a little hint of a rim there, possibly, that kind of thing. But then as you go up that chain, you can see that the third one, if you want to call it that, looks like a little bit more like it's part of a ridge system.
Here.
And so there's so few craters on this guy that we can argue about every one, which is always fun. But yeah, so you can see though that some of these look like depressions and they're very obvious. And there's a good bit of this terrain that we would be able to see that kind of feature if it were there. So there does appear to be areas that don't have strong crater features, and then there's some that do look suspiciously like craters. So.
Right.
Yes, Jordan. All right, so I just have a quick question. Is there topography, and if you can, if this is something for later, that's fine. Is there actually topography related to the ring feature in the center of?
There's topography related to those 8 individual surface units.
Okay.
I'll just stay qualitative.
Okay. All right.
But yes, we're beginning to resolve actual topography there.
Okay. Thank you.
So 67P was also a bilobate object, a very different shape and appearance than what we see. But if we were to separate the 2 lobes for, I guess, either of these objects, the large lobe of 67P is kind of flattened as well. Could these have had a similar mechanism of formation?
Oh, waving my hands in the air. They could have.
Well,
I'm in the camp that you can't trust a Jupiter family comet.
Well,
that,
yeah.
You know, and look what Walt showed us in his first slide. I mean, they look so evolved. The question is whether their shape is started like this and then blistered and did all the other things they do, or whether it evolved to that shape because of some preferential process.
Right.
I don't think we know. What we do know is this did not undergo that kind of evolution.
Yeah. Well, that's fair. And the other thing is that this little terrain splotchiness, it's almost like it's maybe Mike Belton's TELPS model isn't incredibly far off, which is kind of blowing my mind right now.
Which one is that?
It's splat backwards. The idea being that a blob comes in and it strikes the surface, and if the impact conditions are kind of right, and there actually been some modeling of this since 2015. Eric Asfog and Jutsy's been done some of it. Schwartzel, they keep going from very slow impacts to subcatastrophic collisions to catastrophic collisions, looking at what type of shapes you form. And it's almost like the idea that you can take an object and at just the right speed, you can actually have it sort of spread out and coat the surface.
So without giving anything important away, all those papers just happen to be referenced in the submission of science.
Oh, that's perfect.
Okay. All right.
Break time?
Break time. Thanks. Let's thank our speaker one more time. Thank you.